Hi everyone, here I will explain some of the errors commonly found in the homework that I graded related to limit, continuity, and differentiability in multivariable calculus. I call these common errors because they appear in multiple answers. The first one is about epsilon delta statement. So when dealing with the epsilon delta related definition in this topic, it is always necessary not to confuse yourself with the order of the quantifiers. Pay attention to what comes after what. For example, often we see something like, for any epsilon positive, there exists a delta positive such that for any vector p in the domain R with length less than delta, and so on. Here it is known that the existence of delta generally depends on the given epsilon, because it comes after the epsilon. This can really be a source of error unless we read it carefully. Another thing is, whatever your choice of delta is, in this case, always make sure that it is positive. Otherwise, it will become an error. Okay? And similarly, in this definition, even though we have for any vector p over here, that doesn't mean we can substitute any vector for p in this particular case. That's because we first need to make sure that the vector p we choose is indeed in the set R. And then the length of that vector is indeed less than delta. So an arbitrary vector is not enough unless these conditions are satisfied. Alright? This type of errors can always be overcome as long as we read the definition carefully. One last thing about epsilon delta proof is we must not forget to arrange our proof once the delta is found. It is completely okay to work backwards to find the delta, but the graders also want to see whether students understand the logic behind the definition and how the chosen delta works. And that's all for the epsilon delta. The next thing is about limit. There are two things that I will talk about. The first thing is, if a scalar function is less than or equal to another, that doesn't mean its limit is also less than or equal to the other. Because before we can say this, we need to know whether the limits exist or not. If one of them does not exist, then we can't compare them. Okay? That's one thing. For the second thing, always be careful when using polar coordinates to evaluate limits. For example, this function here does not have a limit, but if you use polar coordinate substitutions carelessly, you might find that the limit is 0, which is wrong. Direct substitution for R generally will not lead to a correct result if the theta still appears, because in general, theta is allowed to depend on R. Usually, if we encounter the case where the theta still appears, we instead try to bound the function and try to apply, for example, the squeeze theorem to obtain the result. So be very careful in using polar coordinates. The next thing is about directional derivatives. Firstly, keep in mind that the definition that we use applies to any vector, not just unit vectors, as the directions. If that's the convention in our case, and additionally, the question asks for the directional derivative along any vector, that means we must handle it in the general case. Secondly, the existence of directional derivatives does not imply differentiability. So for example, if we want to prove continuity, sure, we can do that by proving differentiability, but we don't use directional derivatives to prove differentiability, even though in the end, the function turns out to be continuous. So be very careful with the concept. Lastly, to find the directional derivative at a point, please note that there is no reason to use the linear transformation formula unless we know that the function is differentiable at that point. That is according to the relationship between total and directional derivative. So if we don't verify the differentiability first, then the method that we know we can use is, of course, the limit definition of the directional derivative. So in general, be very careful when we want to use any type of formula or shortcut. Make sure first that any condition for that formula to work is satisfied. The next thing is about chain rule. Firstly, if the function f is a single variable, then writing derivative notation such as f subscript x or f subscript t in the same answers is 100% ambiguous and may lead to wrong answers. Consider the expressions like this and like that. What is the difference? Or do they even have meanings? This is totally ambiguous and not a good practice in maths. To overcome this, in a single variable case, just using our old friend the f prime notation, it's quite clear and quite safe without even knowing the name of the variable. But if you really need a name, then you can just specify that first using another variable. Okay? Other types of notations are also a problem when using the chain rule in the multivariable calculus. If you write something like one of these, they can certainly have double meanings, as in noting which variable we must consider, or whether we should use partial notation or not. The solution to this is, of course, write down what are the compositions of the function. It is completely fine to create an additional variable when we write down these compositions, as long as it helps us understand which type of derivatives should we take with respect to which variables. Okay? Next, I've also compiled some careless errors that commonly appear. Firstly, be careful when using case-by-case result. For example, sometimes the directional derivative of a function in the direction AB at the origin is given by this, and at other points other than the origin is given by something like this. This can be overwhelming and can easily get us confused because there are so many cases, so many ifs, and a lot of variables here. That's why if we are being careless or just want to finish everything quickly, we may misread and therefore misuse this type of result. So if we have time, always try not to be in a hurry. Secondly, fix your choice when providing a counterexample. For example, the sole statement a plus b equals ab is neither true nor false. It can be true for certain ab, it can be false for others. So unless we specify what a and b must look like, nothing can be said about the statement. So please emphasize your result carefully. Thirdly, be careful when applying inequality, even though the numbers involved are all positive, or especially when there is an absolute value sign. For example, it is clearly incorrect to say that a being less than b implies a plus c in absolute value sign is less than b plus c in absolute value sign. Or it is also incorrect a squared is greater than a even if a is positive. These small mistakes do happen and they affect the result. And lastly, always pay attention to what you're putting in the denominator. Make sure it is non-zero. Or regarding a square root, make sure the inside is non-negative. These types of errors happen a lot, and being careful is always a solution. Alright? Finally, I will talk about writing solutions in general. Firstly, writing more than one result that are correct generally will not lead to extra mark, especially if some of them are unrelated to the question. What matters is whether we answer the question or not. Similarly, or even worse, If you write more than one result, and some of them are correct, some are incorrect, it may lead to mark reduction instead. That's because the concept is not well understood, and we're not sure which results are correct. So always pay attention carefully to what the problem asks, what the problem wants, and always take time to review the answers. Lastly, explain the reasoning behind your result. For example, if you're using a theorem, mention that theorem. That's because a grader needs to see that you understand why your results follow. Also, the words obviously or clearly or of course do not explain anything at all and will not help you get any mark. You still need to put the reasoning behind the results. Alright? As the last remark, learning by mistakes is always beneficial. So I hope we all can get the better and the best results later on after making any type of errors. Good luck and have a nice calculus journey.